Hi, it's Miss Adams from Flamingo Math. We're looking at Lesson 12, Transformation of Functions. This is the second lesson. Let's look at how we can use transformations and the rules that go with transformations as a rapid method to write expressions for the transformation or find values of that transform function. For example, in example 7, we've got a table of values over here for a polynomial, and we've got that general rule right there where a, b, and c are positive constants. And the graph of g is constructed by applying 3 transformations to the graph of f in this order. So the first thing we want to do is a horizontal dilation by a factor of 3. So in the last lesson, we know that we can do the g of f, or the g of x, is going to be an a value times the f of 1/3, that's our dilation factor, times some x number plus c. The second transformation needs to be a vertical dilation by a factor of 2. So using that same formula, the g of x is a vertical dilation factor 2, that's a, times the f of 1/3 of some x value plus a c value. And then finally, we want to do a vertical translation by 5 units. So that's going to move our c value will move up. So using that same formula, we've got the g of x is going to be 2 times f of 1/3, our x number, plus 5. Now notice here they want us to calculate the g of -6. So if we take our eraser and go back here and plug in -6 here and -6 here, we can use these transformations as a way to locate those values. So we've got the g of -6, which gives us, in the next step, moving down there, the g of -6, we've got -6 divided by 3, that's going to give us -2 in this place. We're still calculating the g of -6, and the g of -6 here. We've got to figure out from the table what the f of -2 is. So the f of -2 is 12. We'll substitute a 12 in here. We don't need the f notation anymore. And we've got 2 times 12, that's 24, plus 5. So 24 plus 5, the g of -6 is going to be 29. And we found that value for the g of -6 using the transformations in the order that they suggested: the horizontal dilation, the vertical dilation, and then the vertical translation. For example 8, we're going to look at the transformations of this piecewise function. Notice the domain is from -4 to 4, and we're looking at a piecewise function that's made up of 6 different line segments. Your job is to sketch the graph of some new function h of x that follows this transformation. So we're going to take our f function and we're going to translate the graph 2 units to the right and 3 units down. And then we're going to talk about the domain and the range of h of x. We know that our rule is going to be subtract 2 from the x and subtract 3 from each y value, since our function rule says we're going to move 2 units left, -2, and 3 units down on y minus 3. So if we take the point -4, 1, and we say -4 minus 2, that puts us at -6, and 1 minus 3, that puts us at -2. We know that -6, -2 is the transformed point from -4, +1. Let's write that down. We started with -4, +1, and that transformed or translated to -6, -2. Now, I'm going to just copy that we're going 2 units down and 2 units right. So thinking along that lines, 2 units down and 2 units right puts you at -4, -4. And we can follow the pattern, the shape of the graph, because all we're doing is transforming that without actually altering or distorting the graph at all. We're just translating it down 3 and left 2. I believe that does that, if I did that correctly. Now we know over here the domain on the original function was between -4 and 4. So the domain on our new function is going to go subtract 2 from the x value, -6, and subtract 2 from the +4. That's our new domain. The range here on the original function looks like the low value on y is -1, and the highest value on y is 3. So our domain, our range, for our h of x graph, we're going to subtract 3 from -1 and subtract 3 from +3. And that does truly match the domain and range of our newly created graph. For the next example, we don't have an explicitly defined function for f, but we're told that we could create h by a sequence of transformations on function f. Let's see if we can figure this out. If the graph of h is a result of a vertical dilation of the graph of f by a factor of 1/2, and then it's dilating horizontally by a factor of 1/3, then translating horizontally to the left 7 units, and finally translating vertically 3 units down. We want to be able to write the equation for h of x in terms of f of x, and I believe we can do that. The h of x is a vertical dilation by a factor of 1/2, and then we have dilating horizontally by a factor of 1/3 means our factor is 3, and moving left 7 means we want to do minus the opposite, so that's going to be plus, and finally going down 3 units. So we should have 1/2 of f times the quantity 3, x plus 7 minus 3 for our h of x function. You might want to look back at the notes from our previous lesson that said anytime we had a horizontal factor of 1/3, that meant that we had to divide our x value by that b value, whatever that b value was. In this case, our b value is 1/3, so x divided by 1/3 is where we got the 3x to come from in that set of instructions or the rule from the previous lesson. Example 10 would be a good one for you to try on your own and then come back and see what happened with our work on the function f of x. The graph of g is a vertical dilation by a factor of a half, so g of x is going to look like 1/2 of f of x, and then it's followed by a vertical translation of 10 units down, so we're going to subtract. Now, in place of the f of x, we want to substitute that polynomial 2x squared plus 6x plus 8, and then distribute that to give us a better, cleaner look of g of x. So half of 2 is x squared, half of 6 is 3x, and half of 8 is 4, so we've distributed the half, minus 10. And then that looks like g of x is x squared plus 3x minus 6. You could take your graphing calculator and first graph your f of x and then graph your g of x and verify for yourself that it did follow those transformations stated. The vertical translation, 10 units down, and the vertical dilation by a half. For example 11, we have a partially completed table for g of x and h of x, and we've got a function rule here for h of x, so we can get started to find the missing values in the table. I believe the first thing I want to do is use the fact that we know the h of 0 is 9, and we can use the h of 0 is 9 as a starting point to say that the h of 0 is 9 when we do 4 times the g of 2 times 0 minus 3. Well, the g, 4 times the g of 0 has to be 12, so the g of 0 is going to be 3. So the g of 0 is 3. That's our first thing we can fill in. Now we could use the fact that the h of 1 is 2, so I'm basing everything off of the h of x since we know these given things. So if the h of 1 is 2, and our function rule says 4 times the g of 2x minus 3. So 4 times the g of 2 times 1, because I'm really substituting a 1 in here. Then the g of 2, 4 times the g of 2, so 2 plus 3 is 5, and 4 times the g of 2 gives me a g of 2 value of 5/4 or 1 1/4. So the g of 2 is 5/4. We've completed the entire g of x table. Now let's look at the h of 3. We don't know the h of 3, but we can use the rule to help us figure that out. So the h of 3 is 4 times the g of 2 times 3, that's 6, and then minus 3. So the g of 6, we do know the g of 6. Oh, the g of 6 is over here. So the g of 6 is negative 2, and 4 times negative 2 minus 3 tells us that the h of 3 must be negative 11. So we've figured that piece out. What's next? The h of 4. So calculating the h of 4 using that same methodology, the h of 4 is 4 times the g of 2 times 4, that's 8, the g of 8. We know the g of 8. It's given here in our table. So 4 times negative 1 minus 3. The h of 4 is negative 7. So back and forth like a little puzzle to solve. We've completed the table using the rule that they gave us here and the known values in the table to complete the rest of the missing pieces. In this example, we'll look at transformations of rational functions. I want to write the equation for the rational function shown in this graph over here and state the domain and the range. It appears if we sketch in the vertical asymptote that we've got division by 0 at -2. And we've got a horizontal asymptote at y equals 0. So you know from earlier that x plus 2 has to be a factor in the denominator. So f of x must be 1 divided by x plus 2. And when the power in the denominator is bigger than the power in the numerator, y equals 0 is the horizontal asymptote. And our numerator has x to the 0 power. The denominator has x to the first power. So that verifies our horizontal asymptote. The domain of our function is all reals except -2. And the range of our function is all reals except 0. In part B, we want to use the grid to sketch a graph of the g of x if we have -2 as our a value and a translation 4 units to the right and another translation of 3 units up. So we want to be able to describe those transformations. Got a vertical dilation. It's also going to reflect over the x-axis. So we could say we're reflecting across the x-axis. We got a vertical dilation factor of 2. We've got a horizontal translation. That's moving 4 units to the right. And we've got a vertical translation. That's moving 3 units up. So try to sketch that graph without watching my work. Okay, here's how I approach that. I looked at this is the function up here, and we want to do all of this stuff to it. So -2 is that vertical dilation and reflection. And then we're going to substitute for this x minus 4, which is going to add 2 to that. So in the end, we're getting a transformation that's going to move 2 units to the right, or give us that vertical asymptote at +2 and a horizontal asymptote at +3. I did do a little bit of calculating to figure that out for the x-intercept. And then stating the domain and the range for g of x. Let's look at that. So the domain for g of x is going to go from -infinity to 2, and then from 2 to infinity. And the range for g of x is going to go from -infinity to 3, and then from 3 to infinity. Finally, on example 13, we want to figure out some of these patterns. If we could state the vertical and horizontal asymptotes for each function using this standard form, which is what we just did in example 12, you can see the vertical asymptote is at 3, and the horizontal asymptote, I've got x to the 0 over x to the first, so y equals 0. In part B, we've got the opposite of 4, so x is -4 for the vertical asymptote, and then y equals -5 is going to be our horizontal asymptote. On part C, 5 minus x means that we're solving 5 minus x equals 0, so x equals 5, and +3 is the horizontal asymptote. And finally, on this one, we see y equals 4 comes first. That's our horizontal asymptote. And same as part C, 12 minus x is 0 when x is 12. So we've got a vertical asymptote at 12. That's the end of lesson 112.